We're going to talk about solubility. This is kind of an extension of equilibrium. So we're going to be using ice tables. And there are two types of equilibrium we're going to discuss here. Solubility is, in other words, how much of what we used to call insoluble compounds, but they're really slightly soluble. For instance, silver chloride. Right? In the first semester, we treated that as just insoluble. I gave you that chart and you said it's either soluble or insoluble. Well, there's a gray area. So we'll talk about solubility, and then we'll talk about one of the ways that you can get insoluble compounds into solution with complex ions. All right. So remember when we were talking about equilibrium when we had K values? And some of those K values had subscripts that were reserved. One of those was SP. That stands for solubility product. Solubility product is just that, it's a product. And remember, if you have a solid or a pure liquid in the equilibrium expression, it's not used in the calculation. So when we talk about solubility, we need to turn on the picture. There we go. We start with the solid, and it's in equilibrium with its aqueous ions. So since the solubility, since the solid is there, it's not part of the expression. And the only thing you have left is the numerator, or the ions and their equilibrium concentrations. So that's a product. That's why we call it a solubility product. And we go back to the concept in equilibrium of the equilibrium constant versus the equilibrium position. And in terms of solubilities, the higher solubility is a different position than a lower solubility. But it doesn't mean that the KSP values are higher in one situation than lower in the other. And the primary reason for that is those powers. Right? When we go back, see these powers here, that really changes the calculation. So the solubility product can't not be equated with higher solubility, except for one situation. If you're comparing solubilities of various compounds, and they all have the same structure to their solubility product, then you can compare the solubility value, the constants, and assess their relative solubilities. We'll have to look at some examples. Solubility is sometimes expressed in terms of grams per liter or moles of solute, molar solubility. If you look it up in a reference manual, very often what you'll see is so many grams of some X per 100 milliliters of water. Generally what you'll see. And that's just a practical application, right? If you're trying to make a saturated solution, then you know how much at that temperature you can put in, just a little bit extra, and you'll be sure to have a saturated solution. And then I've already mentioned this one, they're not equal. Solubility is not equal to solubility product because of those powers. Just an example. So if we were to express, let's take that one, sodium chloride, right? We have a solid, and it's going to be in equilibrium with its ions. right? And let's see. We did Le Chatelier here, right? Yeah, just recently. Okay, we had a saturated solution of sodium chloride. So, and there should have been some crystals of sodium chloride in the bottom. So that expression, that solubility product would be just the simple ion product. But if we take something as complex as, let's see, which one are we using? Sodium phosphate. Like that, then what we get is 3 sodium ions and 1 phosphate. So now the expression for that one becomes to the 3rd power, and then the phosphate to the 1st power. So if we say, what is the solubility of, say, sodium chloride? The solubility would be expressed as, say, let's give it the symbol S, would be so many grams of sodium chloride. Actually, let's make it molar. Moles of sodium chloride per liter. Okay. And this would also be something like so many moles of sodium phosphate per liter. Well, when we try to express that in terms of S, if we put this many moles into solution, how many moles in solution do we get here? Well, we get S, and we get S there, right? If we put this molar of that in solution, we get equal amounts of each one. That means this one's going to be S squared. For this one, though, when you put this many moles in, you're going to get 3 S's here for every one of these, and only 1 S there. So then if we put it in our expression, we get 3S cubed, and then S. So this is going to be 27, right? 27S to the 4th. Okay. All right. Moving on. Calculate the solubility of silver chloride in water. So if the KSP is equal to that value and the equilibrium in aqueous solution would be silver ions and chloride ions. That, and the KSP, and the value is given as 10 to the minus 10. 6 times 10 to the minus 10 would be equal to silver ions and chloride ions. Okay, so I think I've got it animated. Yeah, there we go. So the S here would be, if we had so much of this going into solution, then we would have that much here and that much here. So we would have an S here and an S here, which is S squared. And S squared is equal to this value. We just need to take the square root of it. And that would be 1.3 times 10 to the minus 5 molar is the solubility of silver chloride at that temperature. How about silver phosphate? Let's look at this in terms of let's start incorporating ice into our thinking. This value is 1.8 times 10 to the minus 18. Okay, So if we do silver phosphate, that means we need 3 silvers and phosphate, which we traditionally considered insoluble. And if we start off with 0 here and 0 here, and then the change is going to be minus a certain amount of that, then we're going to get 3 times that over here. And oops, that's not going to work. There we go. And we're going to get one of these over here. So this is not part of the equilibrium expression. So we were just using that to be sure we have these right. Then we're going to have 3s here and s here. And if we set that equal to, well, let's make it complete. 3 of these and 1 of these. Then we can put in values, variables. So we're going to have 3s here cubed and s here. So there we go again. We've got 27s to the 4th is equal to that value. So we'll take s to the 4th is equal to 1.8 times 10 to the minus 18 divided by 27. And then if we want to, we'll just take the 4th root of that. And if we do that, we get 1.6 times 10 to the minus 5 is the solubility. 1.6 times 10 to the minus 5 molar solubility versus 1.3 times 10 to the minus 5. So what that tells us is that silver phosphate is slightly more soluble than silver chloride. All right. Now, that's what we've talked about so far is just putting things into solution in pure water, aqueous solution. Now I have to consider what's called the common ion effect. In other words, if you've already got ions in solution that are common to your solid, then it's going to have an impact on how much will go into solution. Since you've already got some of those ions in solution, you're likely not to get as much into solution. All right, so solubility of silver chloride in water compared to that of silver chloride in an acid solution made with nitric acid. Well, we see the solubility of silver chloride in the first equation, and then the ionization of nitric acid in the second equation. And the question is, are there any common ions there? No, there are no common ions. So the solubility in nitric acid should be exactly the same as it is in water. Okay. You might guess the next one. We're going to assess the solubility of silver phosphate in water versus silver phosphate in nitric acid solution. So if we set up our 2 equations and we combine them, then we reduce them. What you find is that the common ion is not nitrate, the common ion is hydrogen ions. So if we look at that first equation, we've got silver phosphate and nitric acid dissociate into each of those ions: hydrogen, silver, nitrate, phosphate. And then we can combine the hydrogen ions with the phosphates to make hydrogen, monohydrogen phosphate ion. That's all that's happened between this equation and this equation. Well, we know that the equilibrium for this expression, let's see, what's the best way to do it? HPO4 2 minus and H plus and PO4 3 minus. We learned from our acid equilibrium that the preference is over here. Right? It really prefers that one. Because this one has a K3. No, that's not right. A Ka3. And then I should have put that, I'm going to go down this way. So this would have been derived from H2PO4. 1 minus. And this is where the HPO4 2 minus came from. This one had a Ka2. And then we had the phosphoric acid molecule in equilibrium with hydrogen ions and H2PO4 minus. And this one had a Ka1. Well, we know that this K is bigger than that K, and this K is bigger than that K. So that just means with this very small value, it really wants to be over here. Okay. So that's, in this case, the common ion here is hydrogen. And it's driving the reaction. Since this is this is a very weak acid, that's a strong base. And it's going to latch onto those hydrogen ions. Excuse me. Yes. It's going to latch onto those hydrogen ions. And that's going to drive the reaction toward towards solubility, more soluble, right? If we take those hydrogen ions and add them to the phosphate, then that removes phosphate from this equation, and that drives the reaction more that direction. Everybody see that? The equilibrium is shifted toward phosphate ions because they're being removed. This is like another coupled reaction. Those phosphate ions are being removed by conversion to hydrogen phosphate. And that drives the equilibrium toward the right. Okay. So in this case, when you have when the solubility of your solid produces a very strong base as a product, like PO4 3 minus, then if you make the solution acidic, and it doesn't matter what the acid is, make the solution acidic, you're going to increase solubility. That's one of the ways that we get these solids into solution, is when that is available to us, we use an acid. Now, we don't want to use the chloride. Everybody see that? If we use hydrogen chloride or hydrochloric acid, you're defeating your whole purpose, right? Because the chloride's going to combine with the silver ions and drop it out of solution. And that just, that kind of defeats the whole operation. So it has to be the nitrate. All right, this is an extension. Oh, an explanation. How does the KSP of silver phosphate compare in acidic solution? All right, so, well, the KSP values are the same, right? KSP doesn't change. It's a constant, right? That's the point of this slide. As long as the temperature is the same, KSPs are the same no matter what the common ions are. All right. What's the solubility of silver chloride in 100 milliliters of 4 times 10 to the minus third molar calcium chloride? All right. So we're trying to get silver chloride in solution. Okay. We have the KSP is 1.6 times 10 to the minus 10. Okay. And our initial conditions are such that we have introduced calcium chloride. Now, is calcium a common ion? Well, if we take calcium, it's going to react with chloride, right? And calcium chloride is completely soluble, right? So it's not a problem. The chloride, however, is a common ion here. So we start off with none there, and 4 times 10 to the minus 3 molar chloride ions. Okay, so what kind of change are we going to see? Well, we don't have any silver over here right now, so we are going to get some. Okay. So we're going to lose a little bit of this. That's the expression of our solubility. We're going to get some of these, and we're going to get some of these. All right. So at equilibrium, we're going to have that, and we're going to have this. Times 3 plus S. So there's your equilibrium expression. That goes into equating it with this one. So we're going to have S and 4.00 times 10 to the minus 3 plus S is equal to that. Okay. Remember the solubility of in pure water of silver chloride. Let's go back. No, that's silver chloride is 1.3 times 10 to the minus 5 in pure water. Oh, wait a minute. I did something wrong. Of course I did. Calcium chloride produces 2 moles of chloride, right? Okay. So what I'm getting at is we can approximate this by leaving that S out. And we're going to say 8. 8 times 10 to the minus 3 S is equal to 1.6 times 10 to the minus 10. This value was extremely low with pure water. It's going to be even lower with a common ion. So we're going to ignore it for now and solve for S. And S would simply be this value divided by that value, which would be what, 1.6 divided by 8 times 10 to the minus 10 divided by 10 to the minus 3. So this is going to be 10 to the minus 7. And this is going to be a half, right?
Yep. No.
No, 0.05, right? Let's do it this way. I got a better idea. Let's change that to 16. And that makes this one 11. Now we got 8 here, right? And that makes this 2, correct?
Mm-hmm.
So S should be 2 times 10 to the minus 8 molar. Okay, so S is 5 orders of magnitude smaller than that one. So I think we're safe there. And so comparing the solubility went way, way down. And 100 milliliters doesn't matter. Since we were already given the concentrations, 100 milliliters is irrelevant, right? Because we put a solid in that solution, doesn't matter how much it is, right? Because the solid is a solid and its concentration doesn't change. All right, how about this one? Solubility of silver chloride in 4 times 10 minus third molar calcium nitrate. Is that going to have any impact on the solubility at all? No, because nitrate is completely soluble and it's not a common ion. All right, so the solubility is going to be the same as it was we calculated before, 10 to the minus 5, versus this one, which is 10 to the minus 8. So we got 3 orders of magnitude decrease in solubility for our for this situation. Calcium chloride. Okay. Let's talk about Qs. Let me leave that up there for now, in case we need it. When you mix 2 solutions of ions together, what we're getting at here is, can you expect a mixture of cations in one solution and anions in another solution to produce a precipitate? And that's where the Q comes in, because it talks about, or it uses for its calculation, the actual concentrations. And we compare those to the KSPs. So if the Q is greater than KSP, right, that means it's got too much product. Right? So precipitation is going to occur. Got too much product, it's going to shift back this way toward precipitation. Now we're looking at it in terms of, we don't have the solid to start with, we have the ions to start with. And then we say, go working backwards, is that going to produce a precipitate? So if Q is greater than KSP, we should expect precipitation. And if Q is less than KSP, we get no precipitation. Okay. This brings us to the topic of selective precipitation, which was and it may still be used in some situations, especially industrial situations. When you're trying to remove certain metals from solution and you've got a mixture of metals and you want to get them separated from their environment, at least in as large proportion as possible. So we have devised a series of solutions that will selectively remove groups of ions in sequence. And we're going to come to that in a minute. But first, we want to introduce the concept. If we have a solution containing barium ions and silver ions, if we add hydrochloric acid, that will form a precipitate with silver, while still leaving barium in solution, because barium's chloride is soluble. Now we wanted to use the acid. We wanted to get the chloride into solution, but we didn't want any counter cations in there. That's what we're saying with the sodium chloride. Sodium chloride would take silver chloride out of solution. Yeah, it would take silver, but it would leave sodium behind, contaminating our barium. That's why we used a hydrochloric acid. Okay, let's say we have a mixture of these ions, copper 2 plus, mercury 2 plus, and nickel 2 plus. Oh, and manganese 2 plus. Okay. At very low pH, sulfide ion is relatively low in concentration, and only the very, very insoluble mercury 2 sulfide and copper 2 sulfide will precipitate. Here's what happens. We've got H2S in solution, and that gives two H pluses and S2 minus in solution. Okay. If we make this solution very acidic, right, we add hydrogen ion somehow, right? Then we're going to shift it back this way. And that reduces the concentration of the sulfide ions. So that favors the precipitation of only the very, very insoluble sulfides. In this case, mercury 2 plus and copper. Okay. So we find that the overall K for this one is 10 to the minus 20. Right. So if you shove some hydrogen ions in there, you're going to reduce the concentration of sulfide drastically. Then once we get the copper and the mercury out of solution, and we add hydroxyl to it, hydroxyl is going to remove, right? Hydroxyl is going to remove this as water, shifting this direction and increase that concentration. Now we can precipitate the nickel and the manganese with a higher concentration. So as a practical matter, we've discovered that if you make the acidity of the solution about 2 or less, then you can precipitate the copper 2 plus and the mercury 2 plus. And then if we add hydroxide to it, we drive the concentration of the sulfide up, and now the Q is calculated for manganese and nickel as high enough so that it precipitates those also. Okay. Here's the big picture. We've talked about the first one already. We acidify. Well, actually, the last slide we introduced was during the second step, where we add hydrogen sulfide. The first step is to precipitate as many as you can as chlorides. We know some of the chlorides are insoluble, relatively insoluble. Silver chloride, mercury 1 chloride, and lead 2 plus chloride. Those out of those groups, and they're color coded. See, so that first group, the purples, are the first ones taken out with hydrochloric acid. Since we've added hydrochloric acid, now we've acidified the solution. All we have to do is bubble some hydrogen sulfide through it, and that'll take out those very, very insoluble sulfides in that yellow group. There's quite a few of them. And this is a very, very complex mixture, right? If you already know that you only have certain of those in there, you can tailor your precipitations so that you get closer to what you want. Because once you've got the sulfides, for instance, you've got all the sulfides out of this mixture, 1, 2, 3, 4, 5, 6, 7. You got 8 metals in there as sulfides. Then you have to go through a separate step to separate those. But at least you're part of the way there. Then we add the sodium hydroxide. That increases the sulfide concentration and takes out the less soluble sulfides in that kind of orange group. And then if we add sodium carbonate forms a basic solution. And with sodium hydroxide, we're already basic, so that's not a problem. Then the carbonates precipitate the barium and calcium and magnesium. And what do you have left? Well, you have the alkali metal ions, which are soluble in any solution, and the ammonium, which is soluble always. So there you get 1, 2, 3, 4, 5 groups actually that you can work on separately. Now, once you've got them precipitated, how do you get them out of there? Well, you got 2 options. You can decant, just wait for the solid to settle, then decant off the solid, stick your beaker in the oven and dry it. Or if you're in a hurry, you can stir it up really good, right? Get your suspension going, and then dump it through a filter. And then you have to dry the filter and extract from there. Okay. Oh, there's Augusta. We were wondering what happened to Augusta. Is everything okay? Earth Augusta.
Yeah, everything's good.
Okay. So you're going to take the exam on Brightspace, correct?
Yeah, I'm gonna do it after the lecture.
Okay. All right. So we're about halfway through because this is a short slide set. So up to this point, we've talked about solubility of solids in aqueous solution, and how we modify the solution to either reduce the solubility or increase the solubility, and selective precipitation of metals with that sequence of steps that I just showed you. Now we're going to look at formation of complex ions. A complex ion is an ion. It has a charge, which is associated with the entire complex of metal and what we call ligands. The ligands are Lewis bases. They donate electrons. So they're good for bonding with metals. Metals typically make good Lewis acids. So we got this metal ion, and we have one or more ligands added to it. And what we're trying to form is an ion that is soluble in aqueous solution. Right? So what we get with, whereas KSP is solubility product for solids that are going into solution, however slightly, the the constant associated with complex ions is called the formation constant, K sub F. Okay. Now, if your final your end product complex ion has multiple ligands attached to it, to the metal. Say we have a metal and we end up with I don't know, 6 ligands attached to it, and it has a charge. We just make something up. Say it's 3 plus. This is kind of like an acid ionization procedure. 1 hydrogen at a time, 1 ligand at a time. Right? So you would get one of these attached to whatever that charge happens to be, and it would be in equilibrium with that, whatever the ion is. Then you would take this one and add another one. And each one of these would have a K. Okay. Now, as a practical matter, if we are forming a complex ion with multiple ligands, the each one of these Ks is usually large enough so that you essentially end up with the final product, the metal with all of its ligands. For this example, we have, let's see, and I always have trouble naming these things. Did I have that wasn't part of the handout, was it? How do you name these complex ions? Let's see. Well, that's not it. So once we get down to the bottom, I think we would call that tetrafluoro beryllium 2-. Don't hold me to that. I think that's what it's called as the complex ion. So we go through these various steps. We add one fluorine. It has an equilibrium constant. Second one, third one, fourth one. And then overall, right, would be each of the K's times. It would be K1 times K2 times K3 times K4. And if we do that, we end up with an overall K of 10 to the 12th. So that tells me that by the time you get finished making this complex ion, it's essentially everything is BeF4 2-. It goes all the way. And that is soluble. So what we're going to see here is with the formation of a complex ion, everything is in solution, right? So you don't see anything happening unless there's a color change associated with it. The only time you can assess visually the formation of a complex ion is if you couple it with an insoluble solid or slightly soluble solid. Then you can see the reaction dissolve your solid. Right? And the one we're going to do in class, not this, but maybe the next one, next lab after, is determine the solubility, formation constant for complex ion. We've already done it. You just maybe not realize it. Right? When we added ammonia, we got silver into solution. We're forming a complex ion. Okay, so up to this point now, we have two strategies for getting a solid into solution. And it depends on the nature of the solid. If we have a solid that produces a very strong base, its anion is a base, then all we have to do is acidify the solution. And that will take it into solution because the hydrogens will scavenge the strong base and drive the reaction to the right. Okay, but if we don't have that option, the only other option we have is to form a complex ion that is soluble. And the first approach attacks the anion. Second approach attacks the cation. All right. Oh, let's see if Saul Khan has something to say. Let's see, how am I going to get this started? It didn't start automatically. Nope, that's not what I want. There it is.
First, let's calculate the molar solubility of silver chloride in pure water, and then we're going to compare the solubility that we get in part A to the solubility that we're going to get in part B. And in part B, it's no longer pure water. We're going to have some ammonia present. So we take some solid silver chloride, so that's this over here, and we put it in some pure water, and some of the silver chloride is going to dissolve, but most of it's going to stay in the solid form. So silver chloride is only a slightly soluble compound. So there's my little pile of undissolved silver chloride. But some of it does dissolve, and so we get a saturated solution of silver chloride. So there are silver +1 cations in solution, and there are also chloride anions in solution, and we have our solubility equilibrium. To find the molar solubility of silver chloride, let's go ahead and write down our ice table. So our initial concentrations, our change, and finally our equilibrium concentrations. Before we put the silver chloride in, we didn't have any ions in solution. So the initial concentrations of our product are 0, right? We have 0 for the concentration of our ions. Some of the silver chloride that we put in dissolved. So we lost a certain concentration of our silver chloride, and we're going to call that X. So we're losing a certain concentration of our silver chloride. If we look at our mole ratios, for every 1 mole of silver chloride that dissolves, we get 1 mole of silver plus 1 cations in solution. So if we're losing X over here, we're gaining X. We're gaining X for the concentration of silver cations in solution. And since our mole ratios are still 1 to 1, if we dissolve 1 mole of silver chloride, we gain 1 mole of chloride anions. So over here we get a plus X. So at equilibrium, our concentration of silver cations is X, and our concentration of chloride anions is X. So we write our equilibrium expression, and since this is a solubility equilibrium, we're going to write KSP, our solubility product constant, is equal to concentration of our product, so that's concentration of Ag plus, raised to the power of the coefficient, so raised to the first power, times the concentration of chloride anions, Cl minus, raised to the power of the coefficient to the first power. So we can plug in our solubility product constant at 25 degrees. It's 1.8 times 10 to the negative 10. So we put in here 1.8 times 10 to the negative 10. And this is equal to, this would be X times X. So this is equal to X squared. So we can get out the calculator and solve for X. So we have the square root of 1.8 times 10 to the negative 10. So we take the square root of that, and X is equal to 1.3 times 10 to the negative 5 if we round that. So X is equal to 1.3 times 10 to the negative 5 molar. So that's the concentration of, let's say, our silver plus 1 cations in solution. That's also the molar solubility of silver chloride, right? That's how much we can dissolve. So it's a very small molar solubility. So silver chloride is only a slightly soluble compound. Let's see what happens when we have ammonia present instead of pure water. So we have a 3 molar, right? We have some ammonia present now. What happens when ammonia is around silver cations? Right? We get this reaction. So silver cations plus 2 molecules of ammonia give us what's called a complex ion over here. And let's show what's happening. So if we have a silver plus 1 cation, right, we have 2 molecules of ammonia. So let me go ahead and draw in my 2 molecules of ammonia. And this is certainly not drawn to scale. So I'll draw one in on that side. I'll draw another one in on this side. Remember your definitions for Lewis acid, Lewis base, right? A Lewis base is an electron pair donor. And that's what's going to happen here. The nitrogen has a lone pair of electrons, and each ammonia molecule is going to donate a pair of electrons to our silver plus 1 cation. Right, so ammonia is donating as an electron pair donor, so this must be our Lewis base. And the silver plus 1 cation is accepting a pair of electrons, so this must be our Lewis acid. So the formation of a complex ion is a Lewis acid-base reaction. And notice the equilibrium constant for this, 1.6 times 10 to the 7th. Kf is called the formation constant. This is a very high value for the equilibrium constant, right? So the equilibrium lies to the right, and this is a stable complex ion. So any silver ions that are in solution, if you have ammonia present, ammonia is going to pick up that silver ion and essentially remove the silver ions from solution. So if we go back up here and think about our equilibrium, right, if we have ammonia present, we're going to be removing silver cations from solution. right? So we're decreasing the concentration of silver cations. We're decreasing the concentration of one of our products. And Le Chatelier's principle says if we're decreasing the concentration of one of our products, our equilibrium is going to shift to the right to make more. Therefore, increasing the solubility of silver chloride. More is going to dissolve because the ammonia is present, because of the formation of our complex ion. So if we added some ammonia, right, if we added a solution of ammonia here, we could get our silver chloride to dissolve, right, because it's more soluble because of the formation of a complex ion. So let's say we add enough ammonia solution where we get our silver chloride to dissolve here. So that's the idea. Adding our ammonia, right, caused formation of a complex ion which increased the solubility of our silver chloride. So we would expect an increased solubility here of our slightly soluble ionic compound silver chloride. And next we're going to do the calculation. We're going to find the solubility of silver chloride in our 3 molar ammonia solution. Now we've looked at two reactions. We've looked at the solubility equilibrium for our slightly soluble compound, and we've also looked at the formation of our complex ion. Now let's add those two reactions together to get our net reaction for what's happening. All right? So we're going to add our two reactions together to get a net reaction for what happens when you put silver chloride in ammonia. Right? We have silver cations on our reactant side and on our product side, so we can take those out. And so for our reactants, for our net reaction, we have solid silver chloride plus ammonia. And for our product side, we would have our complex ion and our chloride anion. So we have our complex ion, and we also have chloride anions, so Cl-. So that's the net reaction, and if we added those two reactions together to get our net reaction, we have a new equilibrium constant, which I will call K. And if you add two reactions together to get your new equilibrium constant, you multiply the equilibrium constants of those two reactions. So K is equal to KSP times KF. So if you did that calculation, 1.8 times 10 to the negative 10 times 1.6 times 10 to the 7th, you'll get your new equilibrium constant. And I won't do it here just to save some time, but if you do that, you'll get 2.9 times 10 to the negative 3rd. So that's a 9, 2.9. All right, our goal is to find the molar solubility of silver chloride in our ammonia. So we set up our ice table, so our initial concentrations, our change, and then our equilibrium concentrations. And let's pretend like we're starting out with our solution of ammonia and we haven't added any silver chloride yet. So let's go back up here and let's see what our concentration was. Well, we started with a 3 molar solution of ammonia, so let me put that down here. So our initial concentration for ammonia is 3 molar. And if we haven't added any of our silver chloride, then we don't have any of our complex ions. So the concentration, the initial concentration of our complex ion is 0, and we also wouldn't have any of our chloride anion either, so that concentration would be 0 too. So now we add our silver chloride to our solution of ammonia, and some of our silver chloride is going to dissolve, and so we make that concentration X. So we're losing a certain concentration of silver chloride, so we write minus X. Next, we look at our mole ratios. So the mole ratio of solid silver chloride to ammonia is 1 to 2. So for every 1 mole of silver chloride that dissolves, right, we're also going to lose 2 moles of ammonia. So we write minus 2x here. For our products, if 1 mole of silver chloride dissolves, we make 1 mole of our complex ion. Right? So if we're losing X over here, we'd be gaining X over here for the concentration of our complex ion. And same thing for the chloride anion, because our coefficient is a 1. So we're going to gain X for the concentration of chloride anion. So at equilibrium, our concentration of ammonia is 3 minus 2x, our concentration of complex ion is X, and our concentration of chloride anion is also X. Next, we write our equilibrium expression. So K is equal to concentration of products over reactants. So I look at my complex ion over here. So concentration of our complex ion. And we raise the concentration to the power of the coefficient, so to the first power. This is times the concentration of our chloride anion, so times the concentration of chloride anion raised to the power of the coefficient, so raised to the first power. We also have some reactants here. So we leave silver chloride out because that's a solid, right? But we have ammonia. So this is all over the concentration of our reactant. So this is over the concentration of ammonia. And notice our coefficient is a 2. So we need to have a 2 here. Next, we plug in our equilibrium concentrations. So our equilibrium concentration of ammonia is 3 minus 2x, our equilibrium concentration of complex ion is x, and our equilibrium concentration of chloride anion is x. So on the right side, we would have x to the first power times x to the, let me take that out, times x to the first power. Right, all over 3 minus 2x to the second power, so squared. And then we can plug in our equilibrium constant k, which is 2.9 times 10 to the negative third. So 2.9 times 10 to the negative 3 is equal to, on the right side, we would have x squared. So let me write this out. We would have x squared over 3 minus 2x squared is equal to 2.9 times 10 to the negative third. And so what we could do here, these are both x squared, right? These are both x squared, so we could just say that this is all squared on the right side. And then we could take the square root of both sides, right? So take the square root of 2.9 times 10 to the negative third, and take the square root of what's on the right. So the square root of what's on the right would be x over 3 minus 2x. And let's take out the calculator to do the other one. So square root of 2.9 times 10 to the negative third is equal to, let's round that to 0.054. So it just makes it easier here to round that. So 0.054. Our goal is to solve for x. Our goal is to solve for the molar solubility. So we can multiply both sides by 3 minus 2x. So when we do that, right, we would have this. So we need to multiply 0.054 by 3, and if you round that, you're going to get about 0.16, and 0.054 times 2 is approximately 0.11. So we have 0.16 minus 0.11x is equal to x. So we have 0.16 is equal to, we put both x's on one side. This is 1x, and this is 0.11x. So 1x plus 0.11x is 1.11x. And so now we need to solve for x. Right? So we've done our math here. So we have 0.16. We need to divide that by 1.11, and that is equal to 0.14. So x is equal to 0.14, which is only approximate because of all the rounding that we've done. So this is concentration, right? So this is our molar solubility. If we go back up here, x equal to 0.14 molar, right? So that's our concentration of complex ion in solution at equilibrium. That's our molar solubility of silver chloride, right? So it's 0.14 molar. Let's go way back up to the beginning and compare the molar solubilities. Right, so in pure water, the molar solubility of silver chloride is 1.3 times 10 to the negative 5 molar, which isn't very soluble at all. But now we have ammonia present. We've increased the solubility, and we just calculated the molar solubility is 0.14 molar. And obviously 0.14 molar is a lot larger than 1.3 times 10 to the negative 5. So the formation of a complex ion increased the solubility of our slightly soluble compound, silver chloride.
Okay. By about 4 orders of magnitude. All right. Oh, I wanted to make this point. Well, 2 points actually. When you form the, when you combine silver chloride solid and 2 ammonias. Oops, 3. 2 ammonias. And we're forming this complex ion, NH3 twice, and that's that one plus this one. And those are in solution. Notice that this is a Lewis base because it has, if we draw the structure, it has this lone pair of electrons to donate. But if you tried the same thing with the ammonium ion, right, there are no lone pairs to donate. So you can't form this complex ion unless you have ammonia in solution. It's got to be ammonia, not ammonium. Okay. And then I checked on the nomenclature. I mean, it can get complex, but at least for this one, for instance, you start with the ligands, and the ligand name for in the complex ion is amine. So this is diamine, silver ion. Now some will put a Roman numeral 1 in there. You typically do put the charge of the ion, and I wouldn't, because silver can only occupy just 1 plus. That's it. Doesn't have any other choices. So I would say diamine silver ion. Let's see that previous one. I don't think I named it correctly. This one, when we have BeF4 2 minus. Beryllium is going to be a 2 plus, and that's it. So we would say tetra fluoro beryllium. Let's see, beryllium. Did I spell that right? Or does it have 2 L's? Ion. That's it. All right. We're not going to spend a lot of time on complex ion nomenclature. We just need to know how to name the ones that we're going to use so we can talk about them. All right. So Saul Kahn got finished with his discussion. And the relevant species in this dissociation of silver chloride in ammonia solution are derived from these reactions. All right. And those are the Ks for these reactions. We saw the K for the silver chloride solution before. Then we've got the first ammonia added and then the second ammonia added. And if we combine all of them, we should get close to the value that that Saul Kahn came up with. That E is supposed to be a subscript. There. Messed up. And from that point on, and what this actually means is with that K is still kind of low, 10 to the minus 3. You need a very large concentration of ammonia to get the desired effect. Right. So I think Saul used 3 molar. I'm not sure what we're using, 1 molar, 2 molar, something like that. And then if we use, let's see, what molar did we use? Let's say 10 molar. Okay. So in this example, we have 10 molar, and we run through the same set of calculations that Saul Kahn did. And we determine now that the solubility is 0.47. So we've increased the solubility by 4 times. But we had to go from 3 to 10 molar to do it. So my guess is that when you're working with these solutions, you'll be able to smell that ammonia pretty easy. This is a calculation. I think this is the last slide. I was just curious, how much ammonia would be left in solution after that? Right, and there it is. We have 9 molar still left in solution. Okay, so that's all there is to the lecture for solubility in complex ions.